here we are. Great. Okay. Then let's just start. I'm really super happy that we have our new speaker for today. He's from Criteo in France, in Paris, and his name is Otmane Sakhi. He is a research scientist at Criteo currently, but he also finished his PhD jointly with Criteo and the sort of Institut Polytechnique in Paris. And so in like the last years, like all of the work that he's been doing is super relevant to making a lot of the methods that we use or want to use much more scalable and much more doable to actually use at scale. Way more efficient and like also way more effective. And I've, like in the last few years, I've really been like sort of following his work a lot. So I'm very happy that he'll give us a run through of his work and maybe a few some other people's work on how we can solve some important problems. So the floor is yours, Otmane.
Thank you. Yes. So I'll begin. Hello, everyone. First of all, I want to thank Olivier and ShareChat as well for inviting me to the Decision Science Seminar to present in front of such talented teams. It's really a big pleasure for me. As Olivier said, like I'm Otmane, research scientist at Criteo, working on improving the learning of large-scale interactive systems. I did my PhD in recommender systems flavored with statistical learning theory. So the goal was to cast the problem into a decision-making framework and analyze it from a theoretical point of view, but also extend the resulting ideas into a practical large-scale setting that Criteo faces. So today's presentation aims at showing that we actually made a huge step recently in aligning recommender systems with metrics of interest. The presentation is not only based on our work at Criteo, but also different ideas from the literature. And here the goal will be to give an overview of the recipe to achieve practical large-scale reward optimizing recommender systems. Of course, this presentation would not have been possible without great colleagues. So I want to take the opportunity to thank David, Alex, and Nicola, who pushed these pieces of work with me. The presentation will begin by an introduction of the reward optimizing recommendation use case, and especially focus on the large-scale setting. As this optimization is often done offline, we present a general family of estimators that can align the learning objective with the metrics of interest. And we will focus later on the acceleration of training using these learning objectives. And we're going to study two cases, beginning with the one item recommendation, and especially the softmax parameterization. And we want to go beyond that. And of course, we will finish the presentation with a recap, conclusion, as there is no good presentation without proper conclusions. So I think you're all familiar with the recommender system use case, but we're gonna just expose a simple interaction of a large-scale recommender system. So we always begin by a context. It's either a user or a web page that is selected for an impression. So we want to recommend something to this context. We have a recommender system that delivers a recommendation, and we then observe and log a reward. It's either a click, watch time, sales, maybe like engagement for metrics of like long-term metrics. So these three steps actually hide a lot of things underneath, especially for the second step here, because our Rexus delivers a recommendation, but it does it from an enormous catalog, and it should do it actually in milliseconds. So there are a few architectures of recommender systems that are capable of doing this, but in this particular presentation, we're going to focus on the maximum inner product search our approach or architecture, or in the literature, it's also called the two-tower architecture, which can achieve a fast query response from billion scale catalogs. And of course, once we have these three steps, our goal is to find REXs, so recommender systems of these architectures that can maximize the reward here. On this decision making problem can be cast into two different approaches or frameworks. A simpler one, which is called the contextual bandit framework, where the main assumption is that a recommendation that we do right now does not impact the future behavior of a user. And we can also cast it in a reinforcement learning setting where a recommendation can actually impact future behavior, and where we can also optimize for long-term metrics. To ease the exposition, we're going to just focus on the contextual bandit framework here, even though the ideas that we use here can be extended, not easily, but can be extended to reinforcement learning setting as well. So in this contextual bandit formalism, we have a user or a contact that is represented by a feature vector, and we make the assumption that all of the users are independent and coming from the same distribution. We have actions, which represent items or products that we want to recommend, and they're coming from a discrete space with cardinal P. And of course, P is the size of the catalog, and in our settings, it's usually to the 10 of the power of 9 or 12 scale. And here we represent the recommender system as a policy. So with the policy, it means a function that takes the context X and outputs a distribution over the whole action space. By pi theta A of X, we mean this encodes the probability to select action A given the context X. And usually to recommend, we sample actions from this policy given X. Of course, here we do the assumption that these policies are stochastic, but they can also be deterministic as well, because this probability can be just, it can put all of the mass on one action and zero elsewhere. And the signal that we want to optimize is encoded in a reward that is just put in a 0-1 interval here. And the goal is to maximize the expected reward given the context here and the actions done by the recommender system that we want to optimize. Before advancing, let's focus a little bit on what I want, or what I mean by a MIPS recommender system. What I mean here is that the probability of selecting item A given X is influenced by a score, f theta of A and X. The idea is when this score is big, we maximize, or the probability is big, and when this score is small, the probability is small. And the score here that we have for an action in the context is actually decomposable into an inner product between a transform of the user context or user features and a transform of item features. And here we encode the transform into an embedding. So every item A is represented by a feature vector, a continuous feature vector, beta A. And here the parameters we want to learn is this function that transforms X, parameterized by XC here, and the whole item embeddings beta. And once we have this parameterization, actually we can build an index on beta. And with this index, we can identify the top K, so the best items given this score function in big O flock P. So it's sublinear in P, and it's logarithmic even, and it really can achieve fast querying by using this parameterization here. So with this parameterization, with these MIPS policies, we want to maximize the expected reward. Of course, we do not have access to the true reward, but what we do have access to is interactions of a previous system, Pi0. So it's the previous recommender system that interacted with multiple users, did some actions, and collected a reward. And the idea is to leverage this data set here to estimate the average reward here for new systems. So let's dive a little bit more into the estimation. So using this data, the idea is to leverage it to build an estimate. So a point estimate of, or it can be a different estimate, but we focus on estimating the reward here, r hat a of x, and plug it in this learning objective to get an empirical version of it, which is an average over the different contexts that we have in the data, and thus an expectation under pi theta given these contexts that we've seen of this reward estimator. And as simple as it looks, actually different choices of this reward estimator will result in different well-known estimators that are used in the literature. For example, if you put a reward model on R hat, you get the direct method. Of course, it has low variance but substantial bias. You can also have IPS by choosing your reward estimators as like a reward divided by pi0 for actions that you've seen and 0 otherwise. You can have doubly robust there. Of course, these methods, in the worst case, their variance will depend on the catalog size, which can be detrimental in our large-scale scenario. But thanks to recent advances, we can go further. And instead of correcting, for example, the bias, instead of correcting the bias by important sampling in the action space, we can do it in an embedding or a clustering space. So imagine we have a mapping from the space of items to a much smaller cluster space. We can use either marginal IPS or the conjunct effect IPS, which has like state-of-the-art bias variance trade-off, and their variance actually, in the worst case, will be dependent on the embedding space divided by, or the cardinal of the clustering space divided by n. So it's much smaller than what we had previously. So this simple formula here actually can recover a lot of really known estimator. It's simple and really versatile. And for learning, we're going to just choose our favorite estimator here and look for on the policy or the parameter theta that will maximize this objective here. It looks simple, but it is actually infeasible, especially in large action spaces, because this is an expectation over a large action space. Here you can see that this expectation, if you want to compute it exactly, you should sum over all of the actions in your space, and it can be very slow. So the idea is, because we're focusing on maximum inner product search policies, can we exploit this structure to accelerate learning as well? So here we're going to focus on the one item recommendation setting. Here we still have the same goal, is to maximize the empirical version of the expected reward. In the one item case, we want to recommend just the best action. A natural parameterization of these policies is the softmax policy. So you just have your score here, you transform it with an exponential and normalize it to define proper probabilities here. And because the problem is decomposable, so it's a sum over observations, we can use, we can use stochastic gradient descent. And it's really important to use stochastic gradient descent to accelerate or just to scale the learning of with these algorithms. So with stochastic gradient descent, we're interested in the gradient of the objective. So let's look at the gradient of the objective through one observation. We can derive it by the log trick or the reinforce algorithm, which just boils down to having the gradient equal to an expectation under the actions of the reward estimator here, multiplied by a gradient of the log of pi. Wanting to compute this gradient exactly, we'll scale in big O of p because it is still an expectation under pi, and it's just a big sum over the whole action space. If you want to approximate it as well, sampling from a softmax distribution of a multinomial also scales in big O of p. And we also have this gradient of theta of log pi, which has its computation scaling if big O of p as well, because implicitly here we have the normalizing constant that needs to be computed. So we need another trick, or we need another way to define the gradient. We can begin by getting rid of this gradient of log pi here, or getting rid of this normalizing constant from this formula. So we derive a covariance gradient, which pays the price of having a covariance here, which is just a double expectation. So here you have an outer expectation and an inner expectation. But by paying this price, you get rid of the normalizing constant. Our gradient formula here doesn't involve a normalizing constant, but it still scales in big O of p because we have expectations under the softmax policy. An idea would be to use self-normalized importance sampling to approximate these expectations fast. And how to do it is by defining a proposal that can achieve fast sampling and that is close enough to pi theta to have a really good estimate. Just to facilitate the exposition, we make the assumption that beta is fixed. So we only learn the transformation of the context, and item embeddings are coming from, let's say, collaborative filtering or the description of the items. So we will not learn beta, or we will not align betas with the reward that we have. Of course, this assumption can be loosened, but just to easily expose the algorithm, we make the assumption that beta is fixed. And once it is fixed, we can exploit the approximate maximum inner product search easily in training, because we can just build an index on beta and query the top k easily. And that's what we're going to do. We define a proposal which queries the top k items. So you'll have 100 best items coming from this inner product here for the context X, and build a distribution or a proposal which can be seen as a mixture between a uniform distribution, as you have like here, epsilon over p, and kappa A of X, which is a distribution only on the top k. So this is a softmax that can be computed in big O of k, much smaller than big O of p, and constructing alpha k here is done in log of p because we exploit MIPS in training. So the whole proposal construction can be done in big O of p, of log p, sorry. So we can use this proposal with self-normalized importance sampling. So you sample items from proposal, you define your weights here, and then estimate any expectation as a sum, as a weighted sum of your function of interest. With this recipe, we can define the following algorithm. So for every context in the dataset, we query the transform to get the top K actions, build the proposal, sample actions from the proposal, and estimate the covariance gradient. Once we have this gradient, we just update our policy here. So this is a big O of log P iteration here, and the gradient can be computed fast with this trick. And what we can see here with our experiments, like we chose two data sets, the Twitch and Goodreads, with pretty decent catalog sizes. This is close to 1 million, this is 2 million, and we can see that our method, the blue bars are the plain reinforced scaling in big O of P, and these two scale in big O of log P, and we can see that we get up to 25 times speed up, and we always converge faster. So our policies improve the reward much faster than the reinforced one. In the softmax case here, we could achieve fast training by a combination of a new gradient formula, using approximate MIPS in training, and also self-normalized importance sampling to approximate the gradient. This is, however, a trick that is only applicable to softmax policies. So you can see that it's complex and also a specialized algorithm. The natural question that arises is, can we do better? And by can we do better, we go and look beyond one item recommendation. In practice, a lot of recommender systems don't just recommend one item, but we want to serve a list of items here that we call slates. And to extend the softmax into the slate setting, we use what we call the placket-loose policy. So the space of possible slates is much bigger than the space of items that we have, and it's roughly big of p to the power of k, so it's really enormous. Our policies right now should define probabilities over slates and not probabilities over actions. And to extend the softmax, there is a well-known policy called the placket-loose policy, which can be seen as sampling without replacement, the different actions. So you end up with an ordered list of different actions, and its probability can be written this way. And here, instead of looking for the policy that maximizes the reward for one action, we extend also our objective to policies that maximize the reward for slates. And of course, once k is equal to 1, we just recover the previous setting that we had before. Looking at the gradient, we use the same log trick to have access to the gradient, and you can see that right now the gradient is a sum over the items on the slate. And here you'll have an expectation under the slate that you sampled, the reward you had multiplied by a gradient of the log. So you fall into the same problems that you had before, and they're even accentuated because you have this sum over this slate space as well. exact computations of this gradient, of course, is infeasible because it's an expectation under an exponential catalog size. Approximate computations can be done in big O of P, so they're linear in P. But we have an additional constraint, is that this gradient, because it's a sum over K, if you look at its variance, if you just make the assumption that the variants are decomposable, you can clearly see that the variance will scale with big O of K. So the bigger the slate size, the harder this variance is to estimate. So we can say that exact computation and approximate computation, especially from a computational point of view, is infeasible because we want a smaller complexity. And you can just think about maybe extending the covariance formula that we have before. And can we do it? Yes, we can. But it won't solve the variance issue that this gradient will suffer from. So we really need to think a little bit out of the box and maybe reconsider this formula here that we have. So the path that we took is to fully reinterpret policies as smoothed decision rules. And this can be seen in the placket-loose case as the probability of a placket-loose for a slate is either like a product of individual probabilities. So this is an explicit definition of the probability, but it can also be seen as an implicit definition of the probability as an expectation under a Gumbel noise. And if you're familiar with the Gumbel noise, this can be called like the Gumbel trick as well. An expectation under Gumbel noise sampled for each item. So we have P Gumbel noises added to the score here. We compute the score, we add these Gumbel noises to the score, and then we compute a form of arc sort. And if you look at this definition, you can see that a lot of problems are coming from this expression here, because the noise is added in the action space, and so the time and memory complexity are coming from this, because you need to sample P independent Gumbel noise. So this can be done in big O of P, and you should add it here and then compute the arc sort. So everything here scales in big O of P, and especially the complexity is linked to this Gumbel noise that is used here. So the idea is, can we exploit our structure, the structure of the score function that we have here again? And the answer is yes. And what we did is, instead of adding this noise here into the actions space or adding it to the scores of the different actions, we went and defined what we call here the latent Gaussian perturbation policy, where instead of adding noise into the action space, we add noise into the query space. So here you add it in the latent query space. This naturally solves all of the problems because you add this, you sample this noise, which is just a Gaussian. It scales in L. L is much smaller than P. You add it to your query, and you can exploit, once you add it to the query, here you have like a noised query, and you can exploit MIPS in training as well to identify this arc sort really fast. You end up with a really fast sampling, because sampling a slate here just reduces to noise in a query and computing an arc sort. Gradient computations can be done in big O of log P as well, because once you sample your slates here, this is a computation that is done in big O of L. So it's done in the latent space. It's really small. And you only need, this complexity is coming only from the sampling done here. And you also have the, for your gradient here, you also have the feature that it does not depend on the slate size K. So you can increase the size of your slates into 100, 200, doesn't matter. This gradient here will not suffer from increasing the slate size. So here we end up with a much simpler algorithm. There is no defining a proposal for your self-normalized importance sampling. You only need to sample Gaussian noise in the query space, noise your queries, go and look for the slates with maximum inner product search and compute the gradient here, which is done in, all of these steps are done in big O of log P. So you end up with a simpler algorithm, and that actually works for a much general case than the previous one. And when you look at the results in our experiments, we still took like two data sets with big action spaces here. And you can see that here the blue line is for latent Gaussian perturbation with MIPS. The green and the red line are for placket loss, and this is the orange line is for latent Gaussian perturbation without any MIPS acceleration. You can see that LGP performs way better than placket loss, especially in harder cases here, where the action space is really large. So it's faster and better performing than the policy, the placket loss policy that is used in practice. So here we define just a simple recipe. You choose your favorite estimator R hat and define your objective. You parameterize your maximum inner product policy with a latent Gaussian perturbation parameterization. So it's an implicit parameterization that allows you fast sampling and fast learning. You use our algorithm to benefit from a big O of log P training complexity, and you actually obtain reward aligned recommender systems. So as a conclusion to this presentation, sometimes it is better to begin from first principles. Usual parameterizations are not really suited for large-scale decision systems, and you should think a little bit out of the box to make them work. Smoothing the latent space is a good solution, as we've seen with the latent Gaussian perturbation policy. Combining these ideas, we can actually achieve fast, large-scale reward alignment. Empirical extension of these ideas can benefit the Rexit community, because in our experiments for now, we only tried, or we focused on the computational aspect. So for the reward estimators that we used really simple ones. And the idea is to explore the impact of these algorithms or these acceleration methods for larger family of estimators. And that what we can see is that our algorithm is actually applicable to a large family of reward estimators. So we can extend these empirical evaluations to explore different ideas that may benefit the Rexis community. So we have a lot of ideas, and anyone who wants to collaborate, feel free to contact me or contact the team. We're really open to collaborate with the Rexis community and advance together in these problems. So that's it for me. Thank you for listening. You can find all of the references here. And yeah, if you have any questions, feel free. I'm open to answer them.